chapter for synchronization. As we discussed that when there are multiple processes, those are running inside your system. So those processes would actually be, we say that our system is something which can handle run jobs concurrently. Then we discussed about threads, and each thread would be running parallelly to other threads. Now, concurrency and parallelism is maintained between the threads because they share a particular space. So they share some data. And when we talk about data, that is a location. So each and every, like if there are two threads who are sharing the data, they will try to access that particular location. Now, because they are running concurrently or parallelly, we cannot predict at what time task one would try to run to access that particular space, and when task 2 would be able to run that particular execute that particular space. So let us suppose there are thread 1 and this is the shared space. So T1 writes into something, T2 reads from something. Now both are running concurrently, both are in running state. So basically they would be running parallelly if it is a multi-node architecture. They will be running concurrently if it is a single core system, but they are into ready queue or in either waiting state or they are into the life cycle of the process. We never know like at what time T1 would be writing into D, and we don't know T2 would be reading from D at what time. So it may be possible that T2 got higher priority and it start executing first and would try to read from that particular location, share location. So what we need synchronization of different processes so that once T1 writes into D, T2 only read after that. So that one thing is called precedence or the dependency of a particular set of tasks. So it means that T1 should execute first, then T2 should execute first. But there are chances that they may be running concurrently, and we never know the order for multiprocessor environment. So we need some kind of locking mechanism that only one process should be writing into and other should be just reading out. So the locking mechanism has to be there. So the process can execute concurrently, may be interrupted at any time, partially completing execution. So the concurrent access to the shared data may result in data inconsistency. Maintaining the data inconsistency requires mechanism to ensure the orderly execution of the cooperating processes. So that is something which is there. Now, if you remember, we discussed about the problem of consumer and producer. So producer produces something and consumer consume the packet. The producer create a data and put onto the buffer, and consumer reads from the buffer. So this is what we discussed there, that the buffer size is 10. So 10 things could be there. So it's a circular queue basically. So it basically takes 10 things. Now we were managing 2 pointers. One is in pointer and other was out pointer. For that particular solution we discussed is the buffer size is the number of elements could be buffer size -1, because we have only 2 pointer. One is just pointing to the next location where the data could be there, and the out is basically representing where the data is to be taken. So the buffer size was actually the number of elements in that was buffer size -1. Now we can improve that by adding another variable counter. Let us suppose counter starts from count 0, and if the producer produces something, counter is incremented by 1. The consumer consumes something, we reduce the counter by 1. So this is very straightforward. Producer produces something, adds it into the queue, and consumer takes something and take it from the counter. Am I audible? Okay, now what would happen? So we can see that if the consumer is running first, it will add counter, and then the producer would actually add the counter. Consumer would run subtract from the counter. So they are making a balance. Now, per consumer should run after the producer. So if it is like running in that way, all the consistency in the counter would happen. But in case when both jobs are running concurrently or in parallel on multi-node system, what would happen? So we are here discussing about the consistent state of the counter. So we can see that when we say about multi-processing system and they are running multiple jobs concurrently and or parallelly, so in that case, what would happen? What would be the state of counter? Let us suppose counter plus plus is implemented in the machine language like this. So we assign a register a value of counter. So one register is assigned. Then we add in the ALU would actually add the value or with one of this register, and then it is reassigned to this particular variable counter. Counter is basically a variable, so this is reassigned. Now in minus minus, the register 2, it may be register 1 and register 2 are same because we are performing context switching. So register 2 would take counter, then register 2 would be subtracted by 1 and it is uploaded to the counter variable. So these are the two operations those would happen for counter plus plus or counter minus minus. Now consider that count was initially 5. Now because they are running concurrently or parallelly, so that particular thing is, let us suppose they are running concurrently, so the jobs, the task, these set of tasks would be interleaved, means they could, any process can be interrupted at any time. Okay, so they may be interleaved here. So let us suppose the flow of the process may be, this is maybe state, it may be that just first counter plus plus whole this bunch is run executed, and after that this is executing. This is one case. Case number 2, SO, this is executed and then this is another execution done. So counter is 5. Now here the register value has become 6. The other process, the consumer process, is started execution. The register is equal to count. Because the new value has not been written into the counter back, so the current value of the counter is 5 here again. Okay, so the consumer take that 5 value and subtract it from here. Okay, now once it is subtraction is done, now this last statement from both the processes is pending. So producer execute counter is equal to register 1, this statement, and then the consumer would execute this statement from the its own process. Now the counter become from 6. What should be the final value of counter here? 4 or 6? If this is the flow of the program, it should be 4. If we flip it, like we don't know which instruction would execute first and which would execute second, so we don't know whether this executed, let us suppose this executed second and this executed first. In that case, the counter value would be 6 rather than 4 because there are 2 updates to that particular counter variable, and now the second, whatever is last, would be the one which would be actual value. So if we say in ideal case, the value of the counter should be 5 because producer added 1 from 5 to 6 and the consumer took 1 out of it and made it 5 from 6. Okay, so the consistent value for counter was 5, whereas in this interleaved situation, the value of counter become either 4 or 6. We are not sure. In both the cases, both are wrong because it's neither 4 nor it is 6, because that happened because they are accessing the shared base. So they are accessing the shared variable, which is counter here, because 2 processes are entering at same time into the same particular location to write it down, and this particular condition is called race condition. It is very important to understand, and it happens a lot in your process because in kernel there are many, like we talk about preemptive kernels. When it is preemptive kernel, we need to take care of such situations that because our operating system is also concurrently running the jobs, so the order of the task is mattering and they are sharing the spaces, so it matters that we should block the shared spaces by multiple processes, and for that we talk about process synchronization. So race condition is we would arrive at incorrect state because both processes are able to manipulate the variable concurrently. And the situation like this has a several process accesses the multiple same data. So this is basically race around condition that would happen. Now, how to protect it? There is a critical section problem. This is called critical section problem because let us suppose you have 100 processes running and those are sharing data. Now, each process would have a critical section. This is called critical section segment code. The process may be changing common variables, updating table, writing files. When one process is in a critical section, the other process should not be working in critical section. This is what is the critical section problem. So when one started working into it, others should not access it, and it should not enter into that critical section problem. So the critical section problem is designed to solve this. The processes that can use to synchronize their activity so as cooperatively they can share the data. Each process must request permission to enter into the section. So there should be a policy. One process should be going into the critical section part, and this is called critical section problem. And each process would have an entry section, then we have exit section, and then we have remainder section. So how that is managed, here you can look at your process code should be do, you have an entry, then you have a critical section, then you have exit section, and then you have remainder section. So this is the structure of your process, like entry, exit, critical, and remainder section. So 4 divisions are there. Now in critical section problem, 3 things always must be taken care. Mutual exclusion, that one, when process is executing in the critical section, then no other process should be executing. Progress, so in the progress, if no process is executing in the critical section and there exist some processes that wish to enter the critical section, then the selection of the process that will enter the critical section cannot be postponed indefinitely. So it has to be actually given some kind of number. Okay, at this particular time you would be entering into the system or your critical section, so it should not be waiting for indefinitely. Then we have bounded waiting, means interval, time, or turn. So there should be bounded time, like when the next turn would come. Like if there are 2 processes, they want to enter into the critical section, so there should be a bounded turn. Like it should be the process P1 and process P2 both want to enter into critical section. So P2 knows that once P1 execute for one time, I has my next turn is mine, so I will be entering. So that's a bounded basically turn which would be there. The solution to there are many particular critical section problems those could happen. One is as we know that we use fork to create the processes, and fork would return you the PID. In case, let us suppose there is a kernel variable next available PID, and there are multiple processes which are running on the system, both run execute fork at same time because they are running concurrently. Now what would happen? This next variable give the value to both the processes, and same PID would be allocated to 2 different processes. This is also another race condition which can happen. So mutual exclusion is to be provided when we then more than one process which are running either parallelly or concurrently should follow this mutual exclusion principle, that one is allowed to access, not 2 at same time. So this is the process that we are going to discuss. So the example is what I was discussing. The both are trying to access the same location. So it will return 2615 to this also and to this also. So the child of this and child of this would have same PID. And this is a tough problem. We try to resolve it. There are 2 methods. One is there is no preemption. The interrupts are not allowed when one process is running, let it run, let it execute, and process other process would be just executing. So one thing is disabling interrupts, but that would take away everything. The other approach is the preemptive or non-preemptive kernels. So non-preemptive kernels, there is no race condition, because when one process start, it is never preempted. So that's something which is similar to stopping the interrupt. So non-preemptive kernels would not be fit for your responsive, modern kind of operating system. So we have preemptive kernels. Those allow preemptions, but they need to take care about handle this critical section problem, which I'm going to discuss next. So what would happen? We have a Patterson solution for this. So Patterson solution says this is not very good for modern day, multiprocessor system, but would give us a fairly good idea how we can actually control the critical section if we are running two processes. So Patterson solution works on two processes which are trying to access a same particular location. So each process would have the variable int turn. The two processes would share these two variables, int turn and boolean flag. This is an array, this is a variable. So variable turn indicate whose turn is there to enter into the critical section. Variable turn would say, okay, this is the turn for process 1, or it is a turn for process 2. Then the flag is used to indicate if the process is ready to enter the critical section. Flag I means process 1. Flag J means process 2. So if it is I is written, I say P0 process. If J is written, I mean process P1 is there. So we are just abbreviating because this is a two process problem. So if flag I means process 0 wants to enter into the critical section, flag J is 1, true, it means P1 wants to enter into the critical section. The turn means whose turn is, and flag means the willingness to enter into the critical section. Now this is the code. What would happen? This is for Pi. Let us suppose this is for P0. Okay. So Pi is P0, Pj is P1. Now what it will do, whenever it wants to enter into the critical section, it will actually perform this flag I is equal to true. So it means that it wants to enter into the critical section. Okay, but before that, once it makes, it is also a nice process. Why? Because it gives first turn to J process. So the second process, it say, okay, turn J. I gave the turn to J. Okay, if that J process wants to enter into the critical section, it is okay. If the second process is willing, then Pi has given access to J and made turn equal to J. So it basically allocates, says, giving authority to the other process to enter into the critical section. Now, what would happen? It goes to while state. While state says if flag J is true, if flag J is true, and a turn is equal to J, then it is looping and it's in infinite loop here. So it keep on waiting. So what it does then, okay, I'm willing to enter the critical section, but I give first turn to J process, the second process. If flag J is true and turn J is true, turn is equal to J, then this process P0 is waiting. Okay, this would be true only if the other process has intent to enter into the critical section. If this is false, flag J is false, then this while is not true. So Pi would go into the critical section. Okay, so P0 start its critical section, and once the critical section is over, what it will do, make flag I is equal to false. So it says okay, I'm done with my critical section. It's all over. Now the other process can work. I know that now one thing should be clear to everyone here. What is flag I or flag J? Is this clear? Flag I is for P0, flag J is for P1. So
Yeah.
I is equal to 0 and J is equal to 1, let us suppose. Okay. So flag 0 true means P0 wants to execute. It wants to enter into the critical section. Okay. There is another process, which is the second process, and it will want to enter, then it will make this as true. And there is the turn thing. Turn says the processor P0 that I have given turn to processor P1. Okay, so I'm giving my chance. Okay, I gave the other processor chance. Okay, you run first. If you want to enter into critical section, you enter, and after that it will run a while loop. This while loop would be if flag J means the second P1 wants to enter into, it has an interest and its turn is J because this is true. This one is already true because this has made turn is equal to J. So this is already true. If this is true, your P0 would keep on looping here and wait for something to happen. Now let's move to the example. Now this would be much clearer. So I is 0 for process 0, I is 0, J is 1. For process 1, I is 1, J is 0. Okay, so what would happen if flag 0 is true? It has started execution. So process 0 started execution. So flag 0 is equals to true and turn is equals to 1. This is process 0 started. Then it will check the flag. Nothing has started on process 1. So there's no intent of process 1 to go into critical section. So what it will do, flag 1 is equal to true and turn is equal to 1. So turn is equal to 1, but flag 1 is not true because there's nothing, no code executing. In that case, while loop is not executing. While loop is not executing. Since the condition is false, no waiting in the while loop and process 0 enters into the critical section. Now let us suppose once it is into critical section, Pj or process P1 started execution and it says I have intent to enter into the critical section, so it will make flag is equal to true. And when it is equal to true, it will make turn 0. Now the same philosophy that it will try to give turn 0 and but its own flag true. It will check for while loop here. Flag equal to 0 equal to true and turn is equals to 0. Now what would happen? Flag 0 is true. Turn is equal to 0 means it has made it here. Turn is equal to 0. It has itself made it here. So what would happen? This would go into while loop. The process P1 would go into while loop. Once it goes into while loop, waiting for something to happen, the process P0 would start execution and continues until it finishes the critical section. Once it leaves the critical section, it will set flag is equal to 0, flag 0 is equal to false. So when this flag is false, the other process would actually start. So P1 would start. Now it checks again, flag 0 is equal to true and turn is equal to 0. Turn was equal to 0, but flag now has become false. So this come out of that particular loop and it actually started running and enter into the critical section. Now problem 2, example 2, what would happen? Process 0 and process 1. Process 1 started, flag 0 is equal to true, turn is equals to 1, lose the processes here. It does not enter into the while loop. Another process P1 has been context switched. What it will do, flag is equal to true, turn is equal to 0. So it will check for this situation. Check flag 0, turn 0. Now flag 0 is true and turn is equal to 0. It has itself made. So what it will do, it will keep on continue to run. And once it goes to wait state, this check flag would be happening. So flag 1 is true, turn is basically turn is equal, check for turn is equal to 1. Now what is turn here? It is true, turn is 0 because this process has executed and made turn is equal to 0. So now this particular process is allowed to enter into the critical section. So now the third state is, so the flag is 0 because the context switching is happening, so that's why we don't know when the context switching would happen. Okay, interrupt is there. So whenever, let us suppose the interrupt is there, you flag may, one process may lose the processor. So what happens is flag 0 is equal to true. This has executed only one statement. It made it true and lose the processor here. Then process P1, let us suppose this is higher priority, flag is equal to true, turn is equal to 0. Now it will check for flag true, flag 0 true, and turn 0. Turn 0 itself, it has made like that, and the flag 1 is already there. So in that case, it will go into the wait state, continue to loop in. And what would happen when it tries to loop in, the other process, context switching, would happen, and the process P0 would start executing. Now it will execute second statement. What would it do? Turn is equals to 1. It make the second line to run, and now it will check 1 is true and turn is equal to 1. Is it true? Yes, this is true here because it has self-made turn is equal to 1, whereas the flag 1 is always true. So what it will do, it will go to for while loop here. The process 0 would go to while loop. And this now would be actually, when this is happening, now this will go back here to process 1. So it will check the, still on the while loop. So flag 0 is true. This is true. This is okay. But now turn has equal to 1. This is not equal to 0. So it will come out of that while loop. Single while loop is doing so much, and that condition is false. So now process P1 would go into the critical section and performs as is.